There we go. So good morning. We're recording this thing. This is a repeat of yesterday if you're here just because I messed the recording up. Sorry, but I really want it in the repository. I'm working on replacing the existing series. There's some things I'm not happy with. I have 2 years more experience. I think I can explain it better. I think there's some things that I just got wrong in the first series. So doing it again, and particularly in this time of devastation, there's people sitting at home. If you're a tech person right now, you're out of work because your company folded and you haven't picked up a contract yet, that this is something you can focus on for a little bit besides, kind of other things. So, have some fun, ask questions. This is a difficult concept. I call it a dark art. So why are you listening to me in the first place? There's some of my certs. That's not a complete list. You'll see the ones that are current and active in the link down below from your acclaim. And basically, I've been designing, building, and supporting multicast networks now for over 5 years. And you don't spend a lot of time, anytime really, talking about multicast in the Cisco certification program really to get to CCIE level. Yeah, it drops in little bits here and there, like in wireless, but it's not something we spend much time with. Part of that is that, even though we think it's common, because if we run RIP-v2, EIGRP, or OSPF on an Ethernet segment, multicast is happening. Yeah, but it's not multicast routing. Those things are link local. They have a TTL01. They're conversation between routers, and so they're not actually being routed. So this is taking this to the next level, and let's get into some disclaimers. Long and short on this one, Cisco's not paying me or giving me any other inducement. If they ever do, I'll let you know. And I'm basing this on my own experience, but I'm also not doing this based on any company's business process. If I was doing this internally for a company, then it would be. I would integrate a lot more focused on how that company builds it, but I've got to be a little more general in this case because not everyone has the same needs, not everyone has the same capabilities. So there you go. What's multicast? We covered that in part 1. We keep going back to this one, group communication. That's it. And where a group is 0 or more computers, emphasizing for the how many times 0 or more. So there can be a multicast source and no receivers. The multicast source does not at all have to be part of the group. It just sends to the group, and there could be 0 receivers. There you have it. And this RFC 966, 1985, that's the original. It's interesting from a historical perspective, don't spend a lot of time with it, but you see trying to solve a problem, sending communication to multiple machines, but not doing all of them, right? So not doing a broadcast and not doing multiple unicasts. So as you're going to see as we go through this, how with multicast, we're putting more of the load on the network and taking it away from, and this is more like CPU, than we are from the senders and the receivers. What you should focus on for this segment is we're still working on fundamentals, right? And I want you to start thinking about how this works across layer 3 boundaries. And what I mean by layer 3 boundaries is just any layer 3 router. So you're going from one LAN to another LAN. Right? It could just be in your local, you have a small office, you have a couple different VLANs, single router, and you need to do multicast between the different segments. That's what we're talking about. Now WAN, hey, that's extra layer complexity, and there's some good stuff to it. I always emphasize this every course because I want you to be equipped next time someone from leadership comes at you or a user comes at you and says, hey, I want you to do this task in half the time. Like I've either got to drop scope or I'm going to need a bigger budget. And that budget sometimes is a little nebulous because it's sort of like, well, if I'm not working on this other thing right now, somebody else has to. So we may need to backfill a position, right? So, and doing it longer, you may be able to keep the quality, but do it a little cheaper, maybe. right? So these are triple go straights come from project management. There's 3 legs to this stool. You change one, it affects at least one, if not both, right? So if you really want me to do it faster, I may need more money and still have to cut scope. The difference between unicast and multicast is illustrated here. Unicast on your left, multicast on your right. That for every receiver on unicast, I create another stream. So from the perspective of that first hop router, that's the one on the far left, on the left-hand image. Their sender is going to be right on the other side of that. That link to that first hop router has to handle all those streams. So if I had to do it, say like a 2,000 users on a campus, so no WANs involved, and if it's pretty high bandwidth, I may exceed the link budget to do that. I run out of room. With multicast, on the other hand, it's always I send one copy down any link that's interested in the traffic. And I had this one little router I stuck out here on purpose to show it's no copies are going there because no one wants that traffic there. No one's indicated off that router they want the traffic. And this router here, where he's got multiple streams going to different machines, he takes one in, he sends one out each link that is interested. That's it. That's the point of multicast. And another visual here, you're going to see this throughout the course. Again, flatline bandwidth, so taking away bandwidth with multicast versus unicast. And want to keep emphasizing this, always a destination, never a source. A host doesn't own these group IP addresses for multicast, the group does, and the group is a nebulous thing. It's 0 or more devices, so you don't configure the multicast address in the TCP stack anywhere. You're configuring it in an application, if at all. Some applications by default, things like OSPF, EIGRP, that's really an application, right? Or like a RIP. You could do RIP on Linux, on Windows. If I'm doing that, that application owns that IP address, that group IP, right? And it's that range, 224.0.0.0 through 239.255.255.255. Binary starts 110, so this is 224.0.0.0/4. Okay. In part 2, we went over the different IGMP versions starting 1989. So 4 years after they first dreamed this thing up, here we have a working management protocol. And then about almost a decade later, we make some improvements, and then sort of specific multicast gets introduced with IGMP-v3. Since IPv6 is newer, that we took the lessons from IGMP-v2, applied it to multicast listener discovery version 1, and of course we mapped the improvements in version 3 to the multicast listener discovery version 2. There'll be an appendix, there'll be an extra course to talk about IPv6. And this is one of the really key points, unicast versus multicast. In a unicast, I want a web page, so I initiate, I send a GET. I put in a URL into my browser, it does a GET, it does DNS, ARP, it goes through, and in each hop, it's looking forward, going, how do I get there? How do I get there? How do I get there? Multicast, we're doing kind of a different look. We're doing this for what's called reverse fast forwarding, and since the multicast group can exist anywhere, everywhere, or nowhere, it needs to, it's looking back towards the sender. It's always kind of looking back towards the sender. So the receiver is doing its initial join, its initial report. It's always looking back towards the sender. It's kind of doing things a little in a backwards sort of way. And a sender can start broadcasting with absolutely no idea if there are any receivers or where they might be. It just sends. And in that environment, if it's local LAN, what's going to happen is that it sends. Now, a non-IGMP aware switch is going to flood that multicast packet. And because we saw in part 1 that has a special MAC address, every host gets it, sees the MAC, goes, no, don't want that, drops it unless it wants that traffic. With the oversubscription, there may be some times when you're going to take it up to the next, to layer 3, take a look at it and see that, oh, I actually didn't want this, okay? But the sender is broadcasting, the router's also hearing it, and the router needs to decide if anyone needs it outside itself. That's where multicast routing has to get turned on. It's not turned on by default. And there's what we see here, protocol independent multicast is how it gets that receiver and connects it to the sender. I meant that backwards, but whatever. You build distribution trees to forward packets, and they rebuild dynamically. And I'll illustrate that a little bit. We're gonna get through half of this today, and then we're gonna call it quits, and then pick it up on Monday. And a multicast source, so you now have a new route table. So it's your M route table, multicast route. So you've already, you know how to do show IP a route, if you've done a CCNA or better. Now you have show IP M route. And we have a source and a group. So a source is the actual unicast address of the sender. A group is that class D IPv4 address that the group uses to identify the group. Okay. And using the source, the unicast route table is used to determine the interface and next hop where the PIM joins are sent. So PIM join is how we connect routers together, protocol independent multicast. Now, there has been a multicast actual routing protocol, its own routing protocol, but that was dropped. And you got to think about is when you go back to 1985, 1989, how fast were the CPUs? They were incredibly slow by modern standards. They're running a couple gigahertz, megahertz, like 4 megahertz. It's fast, exciting. 4 megahertz, wow. Right now you're like you got a 3 gigahertz CPU, right? Amount of memory, very, very small. These early computers, right? Around 1980, around that period, I think it's like 512K. It's like, wow, you got a lot of memory. You got a whole meg. That's a lot of memory, right? So they just dropped it. In one book I read from about 10 years ago, they said apparently it's still hanging around some places, but it's rare to find. On these PIM joins, we're talking about source and group. The interface, the interface that points toward the source is the incoming interface. So from the receiver's perspective, so last hop router is the one that is attached to the receiver. In his M route table, you're going to do show IP M route. You're going to see a source and a group. Source is a unicast address, so you can tell that's not a class D. It's a class A, B, or C, right? And then you have a class D, which is the group address. And what it shows for an incoming address, that points back to the sender. Outgoing, if you're got a lot of SCIs on a layer 3 switch, or have a router with a lot of interfaces that are distributing traffic, the outgoing interface is going to point out towards the receivers, okay? And there's a loop avoidance check that it only forwards a packet that's received on an incoming interface. So if it comes in a different interface, it's going to drop the packet. And and we'll show some examples why that makes sense. The source is making no effort to get to the receiver. It just sends. The receiver is making the effort to get to the source. The first and last hop routers. The first hop is the router immediately adjacent to the source. The last hop router is immediately adjacent to this last router before you get to the receiver. They are making an effort to try and connect each other, but the source itself doesn't care. The receiver is making, it just starts sending. The receiver has to make a little bit of effort, but not a lot. And how, I mentioned reverse path forwarding. That's this guy. I haven't told you how. He's got an application that wants to use a group. He knows about a sender. I haven't told you how. That he's going to go into unicast route table. He's going to go, it goes out this interface. This is the best path. If this is RIP, this would be perfectly obvious because it's got the least hops. If it's OSPF or ERGRP, combination of bandwidth, delay for ERGRP, bandwidth for OSPF, that cost we add up along the way. This is the better path. That's the way it's going to go. And then the actual traffic, the joins, he's making joins. This last hop router is making joins to this first hop router. He's doing the work. The last hop router, the first hop router, excuse me, at this point, he just gets it, has it, and then there's some magic that we're going to go through later, that how he lets this last hop router know that he exists, the sender exists, this source exists, and then that'll make the effort to connect. It'll send us joins till it completes the tree. Now, problem is, let's say I didn't turn on PIM, and it's a command. You're going to, if you have a multicast running in your network now on SVI or interface, you're going to see IP PIM sparse dash mode. That if I forgot to do it on that interface, the traffic, it'll do the join. The join will happen to here if this guy's PIM enabled. This one won't happen. He doesn't know. He has no way to know that. The traffic's just going to fail. Okay? So that's important to know. If this unicast route fails, so like this link goes down, so this, he no longer has that route, he's going to try and go the other way. Now he has unicast route this way, he's going to try and dynamically rebuild the tree. Okay? And each receiver, each last hop router, this is now a last hop router for this device. This is a last hop router for that device. They're making independent choices of how they get to the sender. So this guy here, this router goes, this is the best path. If there's RIP again, obviously, because, hey, he's got 1, 2, 3 hops to get there. He's got 1, 2 hops to get it. If it's the other ones, well, bandwidth, delay, that sort of thing, are saying, go this way. And each of these routers, when he wants to make the join this way, he makes his reverse path. Did it come in the right interface? And where's the source? What's the best interface to the source? If that doesn't work for some reason, so he thinks he has to go back this way, RPF fails, the join doesn't happen. Now, there's a problem. If I have multiple equal cost paths, the unicast wants to do a hash on the streams. So if I have multiple receivers, particularly from the direction of the sender, he's doing this thing, and he's like, I'm gonna. That's the destination. Well, I should do a hash. I want to go that way. Hey, I want to go. I'll take the other stream. I'm going to go that way. So you may have multiple receivers, and they have different hashes, and so they're trying to do different paths. However, the RPF calculations are pointing one direction and one direction only. So this is how you get some bizarre intermittent failures, inexplicable failures until I told you this. This is why you're here. Excellent, right? So you can do a couple things. I can put some kind of bias, like I could, in ERGRP, I can add delay to interfaces, and so I make this path less desirable. So I still have redundancy. So if this guy fails, that this path is available, and then the two will line up. Or Cisco has this multipath command. So IP multicast multipath. It's a command you enter in the global. on iOS. It looks a little different. So in the ASRs, you actually have to go into multicast configuration, and then it's a subcommand. It may look a little different on different platforms. That's a warning. If I don't have multipath turned on, it's going to go to the highest next hop IP address. So when I'm making my choices here about joins, I go this way because he has a higher IP address from my perspective than he does. That's it. So I can do the multipath command. Now, multipath command is kind of like doing the loose mode for the unicast RPF checking. So this guy can take it either way. Either of those are valid, equally valid paths. I'll take traffic on both those interfaces. Otherwise, he's only taking that traffic. He's dropping traffic, or in this case, down at the bottom. If this is if he's got the highest IP without multipath, he's going to ignore drop any traffic that comes in on this second interface. Okay, this is really important. I'm a huge advocate of turning on multipath. So far, in my experience, I haven't seen it bite me. Certainly possible, right? And you think about it, why I'm blocking traffic. Well, he sends, goes down this link to this guy. He forwards to an interested here. If for some reason he thinks there's an interested traffic here and he sends that way, and then he says, hey, someone's interested in it up there, I can start looping the traffic. When I, kind of like spanning tree, I can build redundancy into my network, but I have to block interfaces to make sure that the Ethernet packet doesn't loop. Now, this is occurring in layer 3. This is not layer 2. In layer 2, it's a spanning tree issue. The traffic's going to go in a particular path based on the spanning tree, and redundancy is going to be handled by, and there is no path sharing, right? Unless this is Nexus, these could be VPCs if these were a VPC pair, right? Really, this could be a VSS on each end, and these can be Nexus running, doing VPCs to this VSS, and that's fun. And in that case, there is no spanning tree issue if this is all layer 2. But layer 3, it's kind of like spanning tree. We got to block something, or we got to figure out how to make it work across multiple links. And so between the sender and the receiver, and this is for source specific and any source multicast. We'll get into some details. This is not bidirectional. We'll talk about that in a future course. Sender to receiver, that's a shortest path or source distribution tree. And in your MROT table, you're going to distinguish that from a shared tree because it has a unicast IP in the first term. And essentially, each router along the path is making that decision. That is the shortest path to that receiver. That's the shortest path from the receiver to the source. Okay, pretty simple. I haven't dealt with this guy yet. Each sender, each receiver, they're making these independently. So when I have the second source, second sender, well, his best path goes dum, 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 dum. He doesn't go over to this guy. That would make no sense unless, right, this was like a T1 and these were all 10 giggers. Sure, with something that goes SPF, that would make sense. And there are in your designs going to be some situations where, I may be taking more hops because of, I've got some backup T1 or something that, and I'm not going that way. Now, be aware, you want to make sure PIM is enabled between all these routers, otherwise this traffic won't flow. Now, there's a shared tree. Now, the shared tree introduces this new concept called a rendezvous point. Even without a rendezvous point, this first hop router, when this receiver sends its report asking for multicast traffic for a group, in your MRoute, it's going to create, for this last hop router, it's going to create an entry for star, comma, and then the group IP. It says, I'm interested in, I have a receiver interested in that group. in its outgoing interface list will be this interface, whatever it is. If he has a lot more interfaces, if they don't have any receivers, interested receivers, they're not going to be in the outgoing interface list. And the incoming interface for this star comma G, the shared distribution tree, points back to the rendezvous point. What I haven't told you, and that's a future topic, is how this guy knows where the rendezvous point is in the first place. So these are two really important concepts. We got about 5 minutes. I don't see anything in my chat box asking any questions yet. Let's talk about some of the differences here. The source or shortest path trees. Well, I'm going to use more memory if I'm to track all the sources. Now, this may not make that much difference. If I have something like, give you an example, something like a music on hold, and I only have like one music on hold source. So we're constantly playing the same music, which is a trademark, right? The same music with the same, thank you for holding, we value you, please stay, blah, blah, blah. I can have one sender. Okay, so that S comma G is not many, right? I have one sender. I may have a lot of outgoing interfaces, perhaps, but I have one. And this is the optimal path to each source from the perspective of whatever router you're looking at. Shared trees, if you only were doing shared trees, and bidirectional does only shared trees, you're not tracking all the sources. And less memory is required because I only care about the groups. With this one, if I've got a lot of groups and a lot of senders, well, I can make that MRoute very, very large. And some things you're going to find as you get into this, there are some silliness that show up. So for home networks, we have a lot of these zero config, Bonjour, SSDP that we have for just so, hey, I set up my AirPrint printer. How does my Apple device know that guy's there? Right, well, it's Bonjour using Multicast. And so that stuff shows up in your MRoute in an enterprise network because that stuff exists. If you have iPads, they want a Bonjour. So, and if you're not careful, if you haven't gone into your printers, and specifically if you're not an Apple house and you don't want Bonjour, you got to go turn it off like your HP printers. You have to go in and turn it off. I always recommended that back in the day. Long ago, they'd be running Apple Talk protocol, and these printers would be running IPX for Novell networks, and they'd have IP, and they might have DLC for VAC systems. Right? You turned everything you didn't need off, right? But the shared tree, since everyone has to go to the rendezvous point, you may introduce delay and the path may be suboptimal. So this is a good place to stop. We'll pick this up tomorrow. Thanks for listening in. And then I'll kind of flip to the last slide. Sorry, let's do this one. There's my YouTube channel. Links you'll find on LinkedIn. Twitter, yeah, too much politics. Probably want to stay away from there, but yeah, you can follow me there. There's my Facebook. I have been posting stuff into Facebook, not as much lately. Kind of focus on LinkedIn right now. Suggest topics, go to my YouTube channel, go to any of the posts on any of the channels. I do check in on them. I do get notified, so if you have questions, whatever, I'll take a look at it. And then catch me on Monday, same time. I'll put a new link up on LinkedIn that you can catch the part 3, section 2. And we'll finish the thing off on Monday. Thank you much, and I will talk to you soon.